Isabelle is 40 years old, and so I would like to talk a bit about how we got here, where we are now, and where we're going. So first, how did we get here? Back in 1986, there was a thing called LCF, that was Logic for Computable Functions. It was a very trendy formalism for a very short time. To implement this logic in a proof assistant, the rules of it were coded as functions in ML, and the so-called tactics were also coded as functions. So a lot of coding for putting in the rules of this logic. My wish at the very beginning was to make something very like LCF, but for Martin-Löf type theory. Of course, I wanted it to be faster and better. I wanted things like backtracking, like in Prolog, which is again very hot at the time. So unifiable variables with search using lazy lists. But to make it work for Martin-Löf type theory, it needed higher order unification. That's when I noticed that this framework, higher order unification, meaning you've got typed lambda calculus underneath, then suddenly you could support lots of different logics, and you no longer would have to write code to build in a logic. You could just write the rules of the logic directly. So you had a logical framework where you could declaratively put in the rules of a wide range of logics that you might be interested in. And again, the very idea of changing your formalism was also very trendy back in the 80s. So these are some of the things that happened over 40 years. I'm not going to go through this list, but you can see different logics being introduced, different achievements. So Isabelle Hall happened much later. Then we got user interface things like Proof General, and later the JEdit, and so on. Now, again, going back in time, 1989, Martin-Löf type theory. These 4 inference rules were given again in declarative form, so no code is being written to execute these rules. We simply state what the rules are. These are the rules for the type of natural numbers in Martin-Löf type theory. Of course, things developed also in the way we specify data structures. Again, not going through the whole list, but you can see where we eventually got things like type classes, probably the first proof assistant with axiomatic type classes. Then the structured is our proof language, and many other things. And I should mention almost all of these things lying outside the kernel, things like the recursive nested data types, recursive function definitions, nominal logic are all outside the proof kernel. Automation was a big deal from the very beginning. The whole point of having Prolog style backtracking was to be able to get at search very directly and easily. And again, here you have a list of dates and a list of things. I, of course, have to mention sledgehammer. Don't be fooled by people who use the term hammer as though all proof assistants have hammers. I guess many proof assistants have things they call hammers. There is only one sledgehammer. Decision procedures are also crucial. Now, most of Isabelle is based on, a good old-fashioned AI approach of heuristic search and heuristic approaches to things. But for certain things, you must have a coded decision procedure that uses an algorithm. So like Gröbner basis algorithms for solving problems over real numbers and so on. The Argo SMT solver, the very powerful real asymptotic package given to us by Manuel Libero. So these are algorithmic and extremely powerful things. What have we done with all these tools? Well, the first big development was in fact for set theory. and again, some big results done in set theory, but then the shift really moved to higher order logic. So real analysis, a lot of abstract algebra, and again, the latest work is formalizing very recent and advanced results, mostly in combinatorics. Another blast from the past. Here is what a proof looked like. I guess this is 1996 or so. This is proving that one version of the axiom of choice, that is AC16, implies another version of the axiom of choice, or to be specific, the well-ordering principle in its fourth formulation. And this is an old-style proof before ISAR, so that's how we did things a long time ago. Another thing down memory lane was the Isabelle logo contest. We decided we wanted a logo. Most of the logos were terrible. We had an election to decide the logo by a system called single transferable vote, or which Americans call ranked choice voting, which is really the only way to do this sort of thing. By the way, I think I am responsible for the two bluish ones on the left. Tobias gave us the Coca-Cola themed one also on the left. So after one round of voting, we were left with these. By the way, the one at the bottom, what do you want to prove today, is based on a Microsoft advertising campaign current at that time. Now you can imagine how things would be if Isabelle was stuck with a logo referring to a 30-year-old advertising campaign. So luckily, when Macarius saw that logo go up as a nomination, and he realized it could easily win, that was when he got his sister, who was an actual graphic designer, to come up with the Isabelle logo that we all know and love today. Anyway, second round of voting. Only Tobias, his Coca-Cola knockoff, survived until in the third round, finally we got our great logo. And thank you to Francesca for giving us this logo. 40 years of the Isabelle distribution. I don't know why it is so lumpy, but there it is. How old? The archive of formal proofs is only about 20 years old, and you can see, I guess it looks kind of quadratic or something. Anyway, growing very rapidly, and that's also very nice. What else has been happening? Well, you can see that we have been verifying things. Semantics of the Java language, formalized programming language theory. Very importantly, some big industrial applications of the SEL for microkernel and Amazon's NIE, not to mention Apple's core crypto, so real large-scale applications of Isabelle to verification. Couple of books by Tobias Nipkow. So, what about formalized mathematics, which a lot of people are interested in? Well, going back a bit, the situation in 2017, there was already a lot of mathematics formalized in Isabelle, and you can see a list of topics there on the right. But people like Kevin Buzzard, for example, were saying, well, it's all 19th century, it's not very difficult, and so on. Now that was a little unfair, not exactly true, but the point was made that one, to be convincing, needed to tackle something close to the research frontier of mathematics. So I managed to get a lot of funding from the European Research Council, hire some mathematicians and try and look into this question. And we got results fairly quickly. So just with a couple of interns, we proved this theorem that every field has an algebraic closure. This is like how you get the complex numbers from the real numbers. This is a fundamental theorem that hadn't been formalized in any proof assistant, but maybe what's more important for us is you see that you make this infinite series of fields, and a lot of people will say, well, you can't do that in Isabelle because it doesn't have dependent types. The thing is, entities don't have to be types, so none of those things are types. They are typed sets in Isabelle, and this theorem has very nice proof by these two students, and was an early sign that we could do the things that we'd set out to do. Additive combinatorics is a trendy new field. I'm not going to go in much detail about exactly what this means, but just to list some of the results, these again, recent deep results that we were able to formalize with great ease. Most of these were really not difficult. So what did I learn from this project and from the ERC's generous funding? First of all, the simple type theory, which we have in Isabelle, in conjunction with a locale, which is simply a context management system, no more than that, seemingly lets you cover almost anything you can dream up, and in a very elegant way. What about set theory? It tends to be needed only in very rare circumstances, normally when you actually want to talk about very technical things related to set theory, like, order types. And then you add a library and bingo, you have the set theory axioms. We get proofs that are legible and they run fast. So we were quite happy with the results of our project. Perhaps more important is the industrial application of verification, and it is really great that we can say that verification has arrived on the industrial scene. It is transforming the practice of software. Slowly but very clearly, the trend has started. So at the SCL4 OS kernel, again, it is both correct, proved correct, and highly performant. Now that is a great claim to be able to make. Okay, 10,000 lines is not a lot, but those 10,000 lines do a lot. And they are correct. Here's just a block diagram of the way they structured the SCL4 itself and the proofs. Another thing, Cherry. Cherry is a hardware design that basically the hardware has to do the job that programmers were too lazy to do, that is to manage memory safely. So it is a hardware designed to protect the computer from the idiot programmers who allow buffer overruns and so on. So this hardware support needs to be verified, and here we have, again, the diagram is showing, you can see where Isabelle is used in the top there to verify certain properties of the Cherry architecture. And there you have some, as you can see, it's quite a big proof. Apple. So what is Apple doing? Apple have finally spilt the beans on how they attain security and reliability for some of their software, which in the past they have left things very vague, and we have this sort of magic Apple touch, but that isn't good enough in this day and age. So the thing that they are using is Isabelle, as you can see in the kind of top middle of this diagram, where Isabelle is used to prove some of the relationships between these different models to obtain quantum secure cryptography for Apple devices. Again, very big proof. Finally, Amazon Web Services deployed in June a thing they call NIE, Nitro Isolation Engine. So this is running on AWS worldwide. I guess millions, I don't know how many millions of instances of this are running, and they have been running very smoothly. This was coded in Rust. Our proofs, however, do not assume that Rust actually delivers on its promises. In other words, the borrow checking stuff in Rust that is meant to guarantee memory safety, we don't even have to trust here because it is being proved, or the full functional correctness is being proved back from first principles through standard formal tools like separation logic and the weakest precondition calculus. Okay, now I think we need to start looking towards the future. What does AI have to do with all this? Well, if you're an Isabelle user, you know there's a wonderful thing called Sledgehammer. But equally, there are things that Sledgehammer cannot do. For example, you cannot just talk to it. It can't sketch out a proof. It can't tell you that you're on the wrong track. It does not give you legible proofs. And you can't tell it to go away and work for 5 hours. LLMs can do all these things. And I would argue this is one of the best applications of LLMs there is anywhere. And why? Well, I won't say that coders are 10 a penny. They're certainly not. But people who can write formal proofs are much scarcer than coders. Being scarce, they're also expensive. And yet LLMs write proofs really well. And the most important thing, you have your proof assistant right there to catch any errors in the proofs immediately. So the LLM starts spitting out some proof attempt. It fails, it corrects it. It can read the error message, it can interpret the error message and try different things so that you get out some code that is a correct proof very quickly. It's also interesting and impressive how much general knowledge LLMs have about everything from mathematics to, say, program verification techniques, or knows what an invariant is, but it also knows what a Galois group is. It is able to translate from other formal proof languages like Mathlib and Holite. And it gives you nice variable names and suitable comments. Here's an example of AI-generated Isabelle code. Now, if you don't know Isabelle at all, this may not make any sense to you, and yet still you can see the variable names look fairly natural. I mean, there could be nothing nicer than X and Y, and then you have the name of the lemma, seems something you can pronounce. And if you do know Isabelle, then you will see an absolutely idiomatic proof structure in which the various steps of this proof are built up one at a time. So this is a thing called a Lipschitz bound for the cosine function, meaning that the absolute difference between two values of cosine is bounded with a single linear factor, namely the sine of 1 times the difference between x and y. So this is a theorem proved. And in fact, just having nice identifiers chosen by the AI is a crucial aspect to this thing being readable. In the past, identifiers generated by computers would have names like G1534. If you replaced all the variables in this by that kind of identifier, you would immediately want to throw this proof away. The AI problems that go right back to the 1960s seemingly are solved here, many of them. It can plan very extensively and in detail. It shows a level of common sense, so it knows what kinds of formulas are appropriate and what are not. It has tremendous linguistic skills, so just as you could suddenly start communicating in Swedish or Hungarian if you felt like it, you can say, oh, here is the proof. Oh, yeah, here's a mathlib proof. I pasted in the buffer. Or here is a hall light proof, and it will just take it and make some sense of it. And you can talk in a fairly common sense way. So if you say, you do this like you did the other time, only you will have to change this and do it as shown in that example. And it is able to look up all those things and somehow infer what you mean. Now, to use any kind of agentic system with Isabelle, you need certain tools. So what they call an MCP server, which is connecting the model to your proof assistant. So from Amazon, we have IQ and IR. These are not the only way, but they are very effective. They have kind of been hacked into the Isabelle front end. So IQ, which works with a running Isabelle session, and IR, which kind of talks to a hidden Isabelle session, or it can talk to your existing one, but it does it without writing into your JEdit buffer. And Amazon Web Services have made all this available to the world as part of the autocorrode verification package that I mentioned earlier, which gives you as well the ability to verify code in Rust and now also in C. Now, the field of AI is moving extremely rapidly at the moment. So just over last Christmas, Joseph Urban was formalizing a book, a whole advanced textbook on topology by Munkris. He did it several times, first in a system whose name I can never remember, and then later he did it in Hall Light, and then later he did it in Isabelle. And many others have formalized lots of things using Isabelle, using AI and Isabelle. So there is a famous, mysterious list of 100 theorems that people have wanted to formalize in their favorite system. So 4 of those were done over the past couple of months. And I can tell you, a whole new library for abstract algebra is in the works, also created by AI. And our archive of formal proofs is now, I have to say, somewhat buried in AI-generated submissions. We also need to bear in mind the drawbacks of AI. People are obviously worried about what it costs also the environment. It's also a bit of a weird interaction mode where it's kind of running maybe in auto mode and kind of thinking and giving its own stream of consciousness commentary, which you can type in questions or instructions, and then you have to wait maybe 5 minutes before it gets to your suggestion or question. The code you get is often over elaborate, so you really need to go back and tidy it up a bit. And of course, it could go wrong. Now, you're not going to get an incorrect proof, but if the definitions are wrong or if the theorem statements are wrong, then your proof will not be good for anything. And because of that, we need to be able to check these proofs over. One could imagine some other AI agent doing that, but really, I think ultimately people have to look at these things. Otherwise, we have no idea what we're getting. It is worth pointing out that AI agents can also make very, very dumb mistakes. Of course, not everyone is using Isabelle, I'm sorry to say, but it really is the best choice for the AI age. The automation it provides allows proofs to be shorter and clearer. They can be found more quickly. With the structured proof language, you can create proofs in a top-down way. So you can plan a proof and have the milestones that need to be proved and leave the gaps to do later. You can obtain, as you've seen, I hope, legible proofs, because no one wants, impenetrable code is not anything that anyone wants to have to deal with. And of course, we have our wonderful sledgehammer tool that we can use it when looking at an existing proof that's been generated by AI, where we see a long proof sequence that clearly could be shortened, and then with one click we can obtain a better proof. That is to say, a nice, short, and simple proof of something that had been proved in a very elaborate way. So, what about the future? Well, the main thing that we need to stress at the moment is engaging with AI. We need to create the best possible AI tools. We need to find ways of teaching this technology, this rapidly changing technology. And we need to decide what we mean by a research contribution in an age where basically a robot can formalize an entire book, and what exactly counts as a significant formalization. And yet formalization of mathematics is still an important goal for us. So we need to design experiments for this new world that we find ourselves in. And also we need a way of coping with the large quantity of, I'm afraid, low quality work that people are generating. Now, it seemingly is necessary to mention lean in particular because there is an impression out there that lean is the only game in town. It has never been like that before. So if we go back, say, to 2017 or earlier, there were many proof assistants. People used them, they exchanged their results, and they were a fairly happy community of researchers. One does see a rather big and unpleasant push that now lean must be used for everything. And I think people should push back and say, wait, we have the right to choose what works for us. In the case of Isabelle, we have the best automation. We have a culture of proofs being legible. We want proofs to be legible, and we don't in any way glory in proofs that are not legible. We can scale to very, very large proofs with still good performance, and we are not stuck with the horrors of dependent types, such as the elaboration process whereby something like 1 + 1 = 2 is expanded into some sort of unreadable horror. I actually regret I couldn't find, again, the thing that 1 + 1 = 2 it actually elaborates to, but it's a doozy. So this is what lean does. I won't read it. You can just look at this, look at all the stuff they are doing just to understand 1 + 1 = 2. And then the question is whether you really want to trust this. In Isabelle, as also in Hall Light and Hall 4, we have simple type theory, and we are proud of it. Dependent types do not work. That is because they require so-called intentional equality. So that is to say, the actual argument of the dependent type needs to be definitionally equal to, say, some other argument, and then you find that, okay, I plus 0 is not equal to 0 plus I, and that can get you into trouble very quickly. Instead of using this system, we use carrier sets. That is to say, you make a thing, say, you can make a notion of a group, say, with an explicit carrier when you need it. And if you have a family of these with the carrier indexed by any set you like, it will work, and you don't have the intentional typing that prevents you from actually using your family as it should be used. All the things that people keep saying we can't have, we already do have. We have a theories of periodic numbers, we have field extensions, we have libraries of abstract algebras, we even formalize schemes. And many of these things we did only to say, well, we can do this. You can also use set theory when necessary, when you're talking about things that only set theorists have available, like ordinal numbers. Now, as speaking to the Isabelle community, we do have to break with old ways and look to the future. Looking at the past, for example, in 1992, there was really a major change when the whole idea of inference rule schemata was changed in Isabelle so that you could have type variables being instantiated. The adoption of the ISAR language, so eliminating the ML programming language from the top level and avoiding the top level and going straight to a proof language instead, was a big break. Then after we had Proof General as a user interface, Macarius thought that his sort of prover IDE was a much better interaction model, but this was also a very disruptive change. Now, there are many, many more things we could hope to have. Now, there are many other things than these. These are just a few suggestions. And of course, we need to be concerned with people who are passing on. We need to transition to a new generation. So that was the past, and we can look forward to the future. Finally, just a few words of thanks. Now, an awful lot of government agencies have given us money over the years, so both the British side, EPSRC, the German side, the DFG, and other like EU programs like ESPRIT and the ERC. And many, many people, very few people were actually mentioned in this talk, but if you contributed a line of any sort of code, thank you very much.